The next gem on our tour of all of the others, it'll be Roman numeral 5 in your notes. This is the gemstone Peridot. Peridot is our August birthstone, and it tends to be a green color with a mixed hue of yellow to it, kind of like an apple, right? The green of an apple. It was confused with emerald for much of history because of the same green, and it was a very valuable gemstone as well. The main source was in Egypt, or was from the country of Egypt, who actually had an island off the coast. I'll say it this way, island in the Red Sea, that was their source for peridot, which they carefully guarded as a secret and a resource for hundreds of years. The mineralogy of peridot and geology is actually incredibly fascinating. It's probably the biggest part of the story today in the notes. Let's go ahead and put mineralogy here. Mineralogy and geology. The mineral of peridot does not have this name. So the mineral, we'll say this way, peridot's mineral name is olivine. And this is one of the most common minerals in the entire structure of the Earth. It makes up the Earth's mantle, but we'll get to that when we start talking about geology. The composition of peridot is MgFe, which occur in the same lattice spot and is along a solid solution like we saw with tourmaline. Most of the time it's magnesium though that dominates. Let's say 90% plus in this space will be magnesium, SiO4. So it's a simple chemical structure. The crystallography is also, fairly straightforward. Let's say crystallography. It tends to form these kind of tabular prisms in the orthorhombic system. So it doesn't have fantastic symmetry. Orthorhombic is one of the lower symmetry, and when it crystallizes really well, you might see kind of crystals like this with some faces and maybe a pyramid at the top. But that shape is not the most common. This is when it's really well grown, euhedral. This is our, nope. We're gonna go euhedral example. But I would say 9 times out of 10, if you were to see olivine, you would see an anhedral, just rounded to jagged fragment of a crystal. That's the most, so we could say often found as anhedral irregular crystals. Our properties in terms of hardness, well, it ends up being, on Mohs scale, it's less than 7. It's maybe 6.5 up to 7 when you're lucky. This makes it fairly easy to scratch. Not as good for jewelry, not as good for survivability in the alluvial environments. So when we mine olivine, most of the time it's not from placer deposit. It has to be hard rock mining. And when it breaks, it does have conchoidal fracture. So the geology of discovering the gem deposits, there's multiple different ways we can get olivine at the Earth's surface. Once it's at the Earth's surface, however, in fact, we should put this down here as like number 1. When it's at the Earth's surface, it's highly susceptible to weathering and breakdown. At Earth's surface, highly susceptible to weathering. So it doesn't want to exist very long in that river alluvial environment. It breaks down because of its hardness and also because of its chemistry. So when it does get to the Earth, when we mine it, we have to find it from some place where it has not been at the Earth's surface very long. We find it in 4 different environments. The most important is in chunks of the mantle, because the Earth's mantle is made up of a rock called peridotite. 90% of peridotite is essentially just peridot. And the problem is the mantle is deep underground. So the chunks of the mantle must be brought to the surface in a volcanic eruption. In a volcanic eruption. And you might think that sounds highly rare, and it is fairly rare to have magma be able to travel that far and carry chunks in it, but basaltic lavas can do this. All right, so it can be found in basaltic lavas. Much of the gem material that we have and that we facet comes from the mantle in these unique volcanic environments. So here's a good example of this kind of material, where in this picture, what we have is, this is our basalt, this is our host. Of course, it's frozen now, right? But it was molten magma, which then turns into lava, and it holds inside of it. And what you'd see if you went to a cliff face. So here's our cliff face, really bad drawing of the cliff face. We'd actually, and all of it's black, okay, which is shit. All this is black because basalt tends to be dark gray to black. All right, so all this is black. Well, if you start to look at that lava flow, there'll be these nodules inside of it of green olivine / peridot. So let's put peridot bearing nodules. Now, a little bit ago, I said that the mantle was made of peridotite. Well, that's a rock made of peridot, right? So there's a connection here to all these things. And where do we see? We see that right here. Okay, and you can see that here's a grain of olivine, and here's a grain of olivine, and they're all just kind of smushed together here as anhedral crystals. That is our primary geologic occurrence of olivine, of peridot. These chunks of the mantle that are brought up to their surface, sometimes we call them mantle xenoliths. So I'm going to add that word to your vocabulary here as well. They're called mantle xenoliths. Xeno means foreign, lith means rock. So they're foreign rocks brought up from the Earth's mantle holding peridot. That's our number one source. Now there's other sources as well. For example, you can have peridot just crystallize from basalt. Peridot crystallizes from basalt. So if you're at Hawaii and you're walking over the basaltic lava flows that make up that island, you might see little green crystals inside the basalt, and they would be little olivine crystals, peridots. Then the biggest crystals, the most fantastic ones that get cut into the biggest gemstones, these are places where hydrothermal fluids end up altering rocks that have a lot of magnesium and can produce big crystals like this one here. This would be from the hydrothermal environment. And then maybe the coolest type of peridot out there comes from meteorites. This will be little d. But if you look at this here, this is iron and nickel alloy grown together. And sitting within that iron nickel meteorite, there's all these crystals of the mineral olivine, and they're all peridots coming from outer space that are 4 billion years old. If I ever, this is like the number one stone I would love to facet someday to get my hands on. Would be so special. So we're just going to say here, we're going to say coolest occurrence. And this is not important for gem purposes just because it's so hard to get the material. Coolest occurrences are in a type of meteorite called pallasites. So these are called pallasite meteorites. And that's all you need to know about that. Now let's go into the next part of our notes. Big B, this is usually color and optics. That's what it'll be here as well. Big B, color and optics. Well, there's not much to say because in this case, olivine is almost always this same color. The greens can change more yellow or a little bit less yellow, but there is not much color variation at all, and it is colored by iron as a major element. Many times in gemstones, it's just these trace elements, the chromophores, that give the color. It's not the case here. It's just normal part of the mineral structure gives the green. The next thing to talk about is optically, we see an unusual phenomenon in olivine, and it's called double refraction. Double refraction is something we can see in low symmetry crystals. And I'm going to show you what double refraction looks like before we actually talk about it. And hopefully on your screen right here, as you look at this gem, the it looks a little blurry when you look into the middle of the stone. The facets are sharp and clean on the outside, but when you look through the stone to see the facets on the bottom side, they're doubled. We did this demonstration in class with calcite and a dot. And when we put calcite above a dot, it made 2 dots. Well, the same process goes on here, where the light is split into 2 beams. And they have different travel velocities, right? The index of refraction is different in the different crystallographic directions. So the light is split into 2 directions that have different speeds, and so they split. So let's see, we could have like a feature here. Well, light comes through that feature, and it goes in this speed and it goes in this speed. So when our eye sees this, we see a doubling effect. And what this can do is it can actually blur the interior of the gem, which is not sought after actually, right? Because it makes things look fuzzy on the inside. Are impurities that can occur in olivine? Well, they are sometimes clean, but they may have inclusions, black inclusions of chromite. These are so black chromite. Or there might be spots inside that are broken, or broken spots. And the broken spots are called lily pads. Lily pads. It's a fun name for the broken spot. Our sources for high-end olivine, well, they are primarily coming from Pakistan and Myanmar. Now, those are 2 countries you've heard a lot over the course of this gem semester, and that's because they are host to so many other types of gems as well. So our primary sources are Pakistan and Myanmar. And the type of geological occurrence here is the hydrothermal variety. So they're making really big, beautiful crystals in the hydrothermal method. In the United States, we do have a fantastic source. There's a place called the San Carlos. It's a Native American reservation in Arizona. And there are xenolith nodules from the mantle that are brought up to the surface in a basalt. And you can go there and mine it, I believe. The Apache people that live on this Native American reservation, they actually work this, and this produces one of the main commercial sources globally. But for the smaller stones. Well, that's it for olivine, aka peridot. See you next time.